Okay, so I would like to thank the organizers for giving me the opportunity to present here this work I did in collaboration with Martin Kind and Juan Pablo Pinasco. We are working at Green Map, which is a non-profit organization dedicated to the promotion of the use of renewable energies in developing countries. So why caring about renewable energy? Well, first because renewable energies are one of the paths paths toward an efficient mitigation of climate change effects. And moreover, they bring a lot of economical benefits, for instance, in terms of creation of jobs. And there was a dramatic fall of technological costs, so that nowadays renewable energies are becoming cost competitive with respect to fossil fuels energy. And this explains why the installation of renewable energy is growing year after year and is projected to keep on growing this way. But the point is that despite all these benefits, private investment remains below their potential in developing countries. And this is mainly due to the fact that investors must face high risks in developing countries, which could be of political, of policy, or financial nature. For instance, there could be a default payments of the government, or there could be issues concerning the exchange rate between the local currency and dollar or euros. And so investors must hedge against those risks, which impact on their costs and so impact directly on the final price of energy. So those risk can be partially mitigated with adequate de-risking instruments, but those de-risking instruments have a cost themselves. So you have to make a good, it would be nice if we could beforehand assess the impact of such de-risking instruments on the final price of energy. But to do so is not trivial at all, because nowadays contracts of production of electricity from renewable sources are mainly allocated through auctions. So in those auctions, bidders are competing to gain the right to sell a certain volume V of energy to the government for a given price. And this price it's this price that's at stake in those auctions. So auctions are a well-studied branch of game theory, are well studied by economists, and it's easy to adapt those results in the context of renewable energy auction, where there could be a large number of bidders heterogeneous, for instance, in their economical size. So that's why agent-based models are being increasingly used to study those kind of auctions. And what I would like to present you in this talk is a simple agent-based model we made with Juan Pablo and Martin, which is simple enough so that we can understand really the dynamic. But the dynamic is rich enough so that our model will be able, I will show you that, will be able to reproduce the trends observed in real auctions. And once I do that, I will add a simple de-risking mechanism and use our model to assess the impact of this de-risking mechanism on the prices. So what is an auction in our setting? So I will consider an auction taking place in several rounds, and always the same end bidders will participate, offering to produce always the same volume V of energy. So the same volume for simplicity. But all the bidders are heterogeneous with respect to their costs. Right? Each bidder has its own costs, C1, C2, Cn. And I will denote by mu I the expected bid of bidder I. Right? And notice that bidders are not allowed to communicate. This is very important. Right? So now, what is around in this auction program? So first, the auctioneer, the government, will announce publicly the total volume of energy to be auctioned. The total volume is willing to buy, and it will also announce the selling price. That is, the maximum price is willing to pay for this energy. Then bidders will submit their bids, and a bid will be drawn at random from a normal distribution with a fixed variance, the same variance for everybody for simplicity again. But the mean value of the bid is this parameter μi, which is characteristic of each bidder. Then once all the bids are submitted, the auctioneer will sort the bid in ascending order and will award the bid starting with the cheapest one until covering the total of auction volume. And then comes the most important part in our model. Bidders are allowed to learn in a very myopic way, in a very simple way, but it's essential. And they will learn in the following way. Assume that a bidder just won the round, okay, just won. So next time he will ask for a little more money. Okay? And on the other hand, if a bidder just lost in this round, then he will ask for a little less money. So the precise amount of increment or decrement of money is computed using the selling price and the cost of the bidder. But essentially, the magnitude is controlled by a single parameter, which we call gamma, and we called it the learning rate. So now to study the dynamic of our model, we consider a very simple setting where each bidder has cost 0, and they bid for now on exactly their mu I. So this normal distribution has variance 0, right? And just for now, just for simplicity. And the selling price, the maximum price, is set to 1. Okay. And here in those plots, I show you the evolution from round to round of the mu parameter of each bidder. So you can see, for instance, that those bidders here, their mu parameter is growing because they are winning. So at each round, they are winning, so they increase their mu. And on the other hand, for those bidders, they are too expensive, so they are decreasing round after round their mu parameter. But the good thing is that at the end, all the bidders end up using the same mu value. They all end up coordinated. They all share the same bidding behavior, which is they either bid 0, their cost. So this means that in that case, energy is cheap, the cheapest possible. Or on the other hand, they end up bidding 1, the selling price, the maximum price. That is, energy is expensive. And the difference between these two behaviors seems to be regulated by the competition level, which is defined as the ratio between the total number of participants, N, over the total number of winners. But this behavior we just observed here is not seems to be quite universal because it's not limited to it does not depend on the initial distribution of the new parameter. For instance, here I show you another set of simulation where the initial distribution is not uniform between 0 and 1, it's different. And it's also robust against noise on the bid. So for this simulation, I use a noise sigma equals 0.1 on the bid, meaning that a bid is drawn at random using a normal distribution centered at mu I, if I'm talking about beta I, with this standard deviation. But still, we can observe that all the beta are coordinating. They all tend to share the same mu value, and this mu value is either 0 or 1. And to see how this final mu value depends on the competition level, I plot here the final mu value in function of the competition level. And you can see that there is a sharp threshold when the competition level is 2, because you can observe here that when the competition level is below 2, then, I'm sorry for that, then you can see that when the competition level is below 2, then prices are going up to the selling price. And on the other hand, when the competition level is greater than 2, prices are going down to the cost. So there is a phase transition. And the good thing is that this phase transition is not only due, we can explain it theoretically by noticing that the distribution of the mu parameter within the beta population solves this equation. Here, the time t means are the rounds, right? And this equation is a Posh differential equation of first order. It's a transport differential equation, more precisely. And the V here has an explicit expression, which is quite involved. That's why I didn't write it here. But studying this equation allows to understand why there is this phase transition when the level of competition is equal to 2. Right. And moreover, we can, in some cases, we can solve explicitly this partial differential equation and get the exact solution. For instance, when the initial distribution of the mu parameter is uniform between 0 and 1, there is a direct mass which is building up in time and whose location is shown by the red dot here. And you can see that this coincides almost perfectly with the agent-based simulation. So this means that really this equation does a good job in describing really the dynamic in our model. So but up to now, we just studied our model in a very idealized setting, right? What happens in a real auction? So to answer that question, we consider the German renewable auction program because it's like a standard benchmark in the literature. And this program has been running since 2015, 2017 with more or less 2 to 3 rounds a year. So there are a lot of data available, and all these data are publicly available on the webpage of the German government. So that's why it's a standard benchmark nowadays. And we concentrate on the solar auction and the wind onshore auction. And here, the gray black background represents the competition level. And you can see that in the solar auction, the competition level was almost always above 2, meaning that the auction was competitive. And at the same time, the mean price of energy, shown in the dashed line here, is decreasing steadily. But on the other hand, in the wind onshore auction, the wind onshore auction were competitive only in the first 3 to 4 rounds, right? And here, in those first rounds, you can see that the price is decreasing. But then, when the level of competition is dropping, the price of the energy is decreasing until sticking to the selling price. And when we simulate our model with a suitable set of parameters mimicking the reality, we see that the result shown here in the solid blue line does a pretty good job in getting the trends of the real energy price. So I think that this model is quite is simple, so that we can really understand it from a theoretical point of view, but at the same time, we can use it to reproduce real observations. So I think it's a good model it's a good laboratory to explore some de-risking mechanism. For instance, we consider here a very simple setting where I assume that the local government got some kind of warranty, for instance, from the World Bank, saying that this guarantee will cover a certain percentage of the auction volume. So this means that if a bidder wins benefiting from this guarantee, then he's assured to get paid. Okay, so this is a de-risking mechanism against default payment. Right? But if you remember that this idea that not all the winners will benefit from this warranty at the beginning, right? So there might be some winners who will win without the guarantee. So you need to take that into account, because if you don't have the guarantee, you need to hedge against the possibility of a default payment. So it's very natural to assume now that each bidder has 2 costs and then submit 2 bids. Then once we do that, the remaining steps are the same as before. The auctioneer will sort the bids and award them until covering the auction volume and using the guarantee when it's available and when the bid requires it. And then there is a learning phase, the same as before. And to test our model, we consider a very simple setting as before, and we observe that really bidders still coordinate. And the level of competition seems to be critical to see whether or the final mu value is close to the same price or close to the cost. Right? So let's see what happens. So we do that, of course, and to get a better idea of the final mean price of energy in function of the competition level and the volume covered by the warranty, I have this plot, which, so here, final price is 1, whereas here it's decreasing from 0.3 toward 0. And you can see that there is still this phase transition when the level of competition is equal to 2. Below 2, the final mean price is equal to 1, meaning that warranty does not impact, even if it impacts in the first round. But as soon as the bidders get fully coordinated, the warranty does not impact you. On the other hand, when the competition level is greater than 2, then you can see that the warranty impacts strongly on the final mean. Yeah, because it can drive the prices from 0.3 down to 0. Right? So there is this strong phase transition. Right? And what could happen if this kind of warranty mechanism is implemented in the German auction, for instance? So we come back to the solar and the wind onshore auction, because we already know that our model does a pretty good job in reproducing the real trends in the prices. And we apply this warranty mechanism. And you can see that in the solar auction, which was a competitive auction, really, the warranty leads to a strong decrease in the prices. Right? On the other hand, in the wind onshore auction, which was competitive only in the first 3 or 4 rounds, the warranty impact on the prices, you can see there is a strong decrease in the prices, but then when the auction stops being competitive, okay, so when the competition level drops and the prices go up to the selling price, then the effect of the warranty becomes negligible. Right? So this confirms this idea that really a warranty matters really when the auction is competitive. So in conclusion, I presented you a simple model of agent-based model, a simple model of auction motivated by renewable energy auction, and which is simple enough so that we can understand it theoretically, but at the same time, it's rich enough so that it can reproduce trends observed in real prices, right? So I think this is a good virtual laboratory to further explore the impact of policy measure. For instance, the impact of de-risking mechanism as we did before. Right? And we saw in that case that warranty really does a pretty good job in impacting the prices only in competitive auction. In non-competitive auction, the warranty impact, but only at first, until bidders get fully coordinated. Well, so thank you very much for your attention, and thank you.